Hi, welcome to assignment 3.4.1b. Um, these are two paragraphs on current. So yeah, let's get started. Because the coulomb is the unit of charge and because currents are charges in motion, it seemed quite natural in the 19th century to define current as the rate in coulombs per second at which charge moves through a wire. If Q is the total amount of charge that has moved past a point in the wire, we define the current I in the wire to be the rate of charge flow. So, so electricity is essentially electrons flowing in a wire. Um, so electrons each has a certain charge, and and the unit for charge is coulomb. So I like to think current as um the speed of electrons moving essentially. So um since current is the unit of current is ampere, which is coulomb over second. um the greater the current, that means there are more coulombs of charge moving through a certain point in the wire. um that means more electrons are moving through that point in the wire, which is going to have a greater charge flowing through that point. So for a steady current, which will be our primary focus, the amount of charge delivered by current I during the time interval delta t is Q equals I times delta t. So yeah, um so so as I said earlier, I or current is pretty much speed. So speed times time gives us distance, which pretty much is charge in this case. And the SI unit for current is the coulomb per second, which is called the ampere A. Yes, I already talked about that. So the next paragraph is after I read it, I thought it's like really interesting, so I want to talk about it. Do charges slow down after passing through the bulb? This is a little trickier, so consider the fluid analogy shown in figure 27.15. So it's right here. Um, Suppose the water flows into one end at a rate of 2 kilogram per second. Is it possible that the water, after turning a paddle wheel, flows out the other end at a rate of only 1.5 kilogram per second? That is, does turning the paddle wheel cause the current to decrease? So, since I already knew that electric current is a bunch of electrons flowing in a wire, and this paddle wheel kind of kind of resembles a light bulb. So it's a resistor. So once I had the question of whether like once the electrons move through that light bulb, does it slow down? So this analogy explains it perfectly. So like think about the water flowing in. So when the water is flowing in this way, like although although we know something has to be used since this turbine is now turning. um Imagine like if water's flowing through this turbine, but water can't get destroyed, like they can't get like compressed, or like, well, they can get compressed, but um they're pretty much like the same density, I would say. So is this the speed flowing in and flowing out is pretty much the same. So that means the current, after the current flows through a light bulb or any resistor, the current doesn't decrease, but the kinetic energy carried by the electrons is taken up by the turbine or the light bulb. So once the electrons flow through this light bulb, the electrons collide with the resistor, which in this case in the light bulb, it gives off heat or like light. So yeah, I thought that's just really interesting because it helped explain a question I had earlier. So this is the question I picked about current. So a car battery is rated at 90 amp hour, meaning that it can supply a 90 amp current for 1 hour before being completely discharged. If you have your headlights on until the battery is completely dead, how much charge leaves the battery? So, so we know amps, 90 amp means 90 coulomb per second. And then we have this 90 coulomb per second thing flowing for an hour, which translates to 3,600 seconds. So, like I said earlier, speed times time. So, we just use 90 coulomb per second times 3,600 seconds, and these two cancel. So we're left with 324,000 coulomb. So it kind of makes sense because the I didn't actually understand like the measurement of how big a battery is, but this explains it. Like if you have like a current flowing with electrons flowing out, and imagine like water flowing out, like the analogy we had earlier. So imagine like the battery is like a water tank and you got water flowing out. um it's gonna deplete like the kinetic energy, like once it flows through like the headlight in this case. So like after all the water like flows through, and like eventually the kinetic energy is gonna get depleted. So the speed, like the rate at which the energy is like flowing out times the time equals like the total energy the battery can carry, really makes sense. Thanks for watching.